And all molecules have potential stored energy and bonds between them. And then what's fascinating is most of the molecules that we're talking about, from DNA to fats to carbohydrates to proteins, all have these carbon-carbon bonds. And then the carbon-carbon bonds are the real critical bonds for retrieving energy out of the molecules. And they were created ultimately by photosynthesis of plants and trapping solar energy in those carbon-carbon bonds. So basically, the energy we use from food material comes from the process of photosynthesis that plants use to trap solar energy to attach those carbon-carbon bonds together. So, interesting cycle in the world around us. So one of the things that we're concerned about is that through the digestive process and through a food supply system, we actually have the ability to require the basic energetic needs that we need. So unfortunately, if we were to look at the world as in a big picture, about 1/3 of the people that live on Earth have the energy resources they need to maintain themselves. And about 2/3 of the people on the Earth are malnutrition because of food disparities in terms of food supply. So the way to think about it is that we measure energy by a calorie. And by definition, a calorie is the amount of energy to convert 1 gram of water 1 degree. So if you were boiling water, right? So what we do because of numbers and because people would just freak out is we convert calories to kilocalories when we label things. So for example, if you looked at a Snickers bar, it would say 450 calories, but that's really 450,000 calories, which that number would be big, and you got to go, So we've converted it to kilocalories. So when we think about diet and labeling in the United States, we use kilocalories. And kilocalories is the amount of energy required to change a kilogram of water 1 degree Celsius. But it's the same thing, we just multiply it by 1,000. And so then the way we try to calculate kind of what the basic needs are is a basal metabolic rate. So ideally, everybody on Earth should have an adequate food supply to basically maintain their body, and that would be a basal metabolic rate. So when that doesn't happen, then we end up with malnutrition and it leads to significant problems. So the way to think about it, BMR is the minimum resting energy expenditure by an awake alert person. So the average BMR, and this data is adjusted for gender and it's adjusted for age, but the pattern is the younger you are, the higher your BMR. Men have a slightly higher BMR than women, and as you age, BMR drops, which is why it's easy to put on weight as you age, because your average metabolic rate is actually dropping because your body's not doing as well as making new cells all the time and doing its job. So the average BMR is about 70 calories per hour, or about 1,680, 1,700 calories per day if you rounded it up. Okay. So the way we calculate that, you can do it mathematically. So if you assume that we're using the average amount of carbohydrates, lipids, and proteins in a catabolic process to generate energy, then we would basically generate 4.8, or we can round it up to 5 calories per liter of O2 consumed. Then all we have to do is measure the amount of O2 that somebody's consuming. So if you were in a research facility where they actually are calculating BMRs, they put something in your mouth that you breathe through, and that actually calculates the amount of oxygen you consume. And then once you know the amount of oxygen consumed, then you can look at the amount of calories being produced. That's basically the way they do it. So you may have seen, particularly in exercise physiology, where somebody's on a bike or treadmill and they have this thing in their mouth, and they're running. They're actually looking at O2 consumed to actually calculate the amount of calories being consumed. And if you buy some of the exercise equipment that you can get on the market, like a treadmill now or something, they've used that research to figure out the basic caloric use by somebody on the treadmill at a given time. That's why you can put your body weight in, and it'll roughly calculate how many calories you're burning as you're on the exercise. It's all done from that experiment, from using this idea. So as I said, BMR is actually influenced by age. So with age, BMR drops. The gender bias is men have a higher BMR because they have a higher muscle mass than most women. And then physical condition, and that's the interesting thing, is that the more physically fit you are, the higher your BMR is. The less physically fit you are, the lower your BMR is. So it's like a double whammy, because if you start putting on weight, and you don't exercise, then your BMR drops, and it's easier to put on weight. And so you have to reverse it by increasing your BMR through exercise. And then it's genetics as well. So some people have high BMR, some people have low BMR as natural. Okay. So basically, what we're going to do is we're going to absorb the end products of digestion, and then that's going to allow us to do muscle contraction, to do secretions, to do active transport, and supply the energy. Then the other thing we do with the molecules is we use those for the structural components to make new material to replace cells through mitosis and cytokinesis. So just as a quick review, we completely replace our skin surface every 25 days. So we use an enormous amount of energy in the process of mitosis just to make sure that we have this really good impermeable layer of skin so that we can actually be a walking pond supplying an environment where our cells are surrounded by fluid. And so if we have all the energy on board to do these metabolic processes, and we have all the structural components on board to do the normal replacement and repair, so 2 million red blood cells per second in addition to the skin, then any excess we take in is going to be stored for a later day. And that's because for most of our life on Earth, food was not readily available like it is today, where we can go to a grocery store as long as we have the financial resources and buy anything we want any time of the day. And so for most of our history on Earth, winter was a bleak time. And so the body's designed to acquire and store resources during periods of good time, like in the summer and fall when food is more available, and then to live off those resources during winter when food was harder to come by. And so one of the things we see, particularly in developed countries, is an increase in adiposity due to the fact that we no longer have those peak periods of time that we one time had. So it's tricking the body into it. So that's kind of interesting because when we look at weight loss, if you use fasting as a model to try to lose weight, your BMR drops. So when you stop taking in as many calories, your body adjusts your BMR because it doesn't want to give up those reserves that it's used to having for long periods of time. All right. Oops. So what we're going to do is we're going to look at some metabolic processes in the human body. Certainly we're not going to have enough time to cover them all in great detail. So we're going to try to create a foundation for these metabolic processes. Maybe you can take a biochem class or nutrition class where they expound them. So metabolism is the ability to acquire and use energy from the environment. Then we use those metabolic processes that occur in our cells, tissues, and organs to drive biochemical reactions that allow us to maintain structure and provide energy. And so there are actually two types of metabolic reactions you can think about. Catabolism, which is the breakdown of large molecules into simple ones. So that's exactly what the digestive system is designed to do, is to be a giant catabolic reaction chamber allows us to take in pre-made organic molecules and break them down into their simplest components. And because you're breaking bonds between carbon molecules, you release the energy that the plant's trapped in the carbon molecule. And so that allows us to acquire energy from carbon-carbon bonds. And then what we're going to do is tie this energy release from catabolic reactions to anabolic reactions, where we take simpler molecules and construct larger molecules out of them, and that process requires energy. So what we try to do is tie catabolic reactions to anabolic reactions in the body. So the simplest one to think about is just the molecule that we use to transfer energy. So when we make these carbon-carbon bonds, we release energy. And then the energy is divided into kind of two groups. The energy that's used, and then what we would consider as waste energy, which is low-grade energy that we really can't use effectively. And so we would refer to this as heat energy. And then that maintains body temperature. Okay. So the way to think about it. So if you get really cold, what's your body do? It begins to shiver, right? So because if we use more ATP, we get more waste energy. Then when we get really cold, we get random contractions of skeletal muscle. Remember, power strokes, every power stroke a muscle uses requires the consumption of an ATP. And so we shiver to drive metabolic processes upward to create more heat energy to recover the heat we're losing. And so it's just kind of a cool process. And basically because, like we did in lab, the enzymes that run our metabolic processes work maximally at 37 degrees Celsius or 98.6. So we try to maintain that. So the inverse would be to be like a reptile or a fish, whereas body temperature drops, your metabolic rates really slow down. So it's always fun in the fall or early spring when snakes become more active again, if you're out in areas, because they'll crawl onto roads and rocks and try to run. And if you're there when it's really cold, they're real lethargic and they can't move very much. And then as they warm up, they move more. So we try to maintain our capabilities. And so what we do is this energy that we use, we harness into ATP. So we take an ADP molecule, we add a phosphate to it, and we get an ATP. So is this a catabolic or an anabolic reaction? It's an anabolic reaction. So if we're breaking these carbon-carbon bonds, is that a catabolic or an anabolic reaction? Catabolic. So we're using a catabolic reaction to release energy to drive an anabolic process. Okay? So then we use this as our energy currency, so that if we need energy, then we can convert it back to ADP plus phosphate. So this is a catabolic reaction. So when we have additional energy, we can make ATP. Then when we need to use energy, we can use the ATP. So it just so happens that ATP has phosphate-phosphate bonds, and the third bond is really high energy. So this is a real high energy bond. So we use ADP and put a phosphate on it to store energy in this bond. And then when we need the energy back, we take the ATP right there. And then the rest of the molecule, years ago I remember what it was like, and I just dropped this. I just need some coffee. Okay, I'll keep my dates in mind. All right. So then putting this together is the fact that that we absorbed the material through our gut lining and put it in our capillary beds. And then we transferred it to the liver where the liver processes it. And then we transfer it to our cells via capillary beds, so that within capillary beds, the end products of digestion come out of the blood and into interstitial fluid. So our amino acids, our fatty acids, glycerol, glucose, and then we transport those across the cell membrane to get it into the cytoplasm of the cells in our tissues. And then within the cytoplasm of the cells of our tissues, we can use all these products if we have to make energy. So we can use amino acids, we can use fatty acids, we can use glycerol, we can use simple sugars, and we can use nucleotides to make energy. The body's favorite choice for making energy is simple sugar. After we've consumed all the simple sugar, our next choice would be fatty acids and glycerol. And once we've used all that, our last choice would be amino acids and nucleotides, because we end up with a waste product of nitrogen that becomes problematic for the body when we do that. But that's why if you look at the pictures where people are malnourished and they're starving to death, they have no muscle mass left on their arms and legs. They have self-digested their own muscle mass to try to drive metabolic processes. So even in cultures like this with eating disorders like anorexia, I'm a people watcher, so if I go with my wife to the mall and shop, I just sit and watch people. You see these young gals with legs that aren't as big as my forearm, and you know they're anorexic and they've used up all they're using up all their skeletal muscle to use ATPs to make energy. So the take-home message is our best way to do that is within the mitochondria. And it's the mitochondria's ability to do that requires us to intake oxygen. So the thing that, if you kind of reduce the human body to simple processes of metabolic activity, is that we have a respiratory system that we're going to cover in the next unit to allow us to exchange gases. Then we have a circulatory system that we're going to cover in the third unit that moves those gases to the cells. And the only place we really need oxygen in our entire body is a mitochondria to make energy. Okay. So if we have these nutrient pools that we can use to produce energy, then we get ATP. And then from the ATP, we can do all of those activities that we talked about. So we can do locomotion of the body, we can do contractions within the body, we can do intracellular transport of material, we can do cytokinesis and make new cells, we can do endocytosis, ectocytosis, take things in and out of our cells. So if we have the ATP we need for this, then the other thing we do is use the ATP to provide growth and maintenance, to produce structural proteins, enzymes, lipids, carbohydrates, for producing new cells. And then if we have all the energy we need for this, we have all the energy we need for that, then the ultimate goal is to store those resources for later use when we might not have enough energy. All right, so when we look at carbohydrate metabolism, then simple sugars are small molecules that can move through membranes fairly readily. So a simple sugar is very hard to use as a storage molecule. So what we want to do is we want to take simple sugars and complex them into large molecules that are more easily stored. And then we want to have the ability then to take those storage molecules and break them back down. So as we're going through these reactions, then the one thing that you need to make sense out of is the ending of the word. So if we use the ending of the word lyse, it's going to be a catabolic reaction. And if we use the ending of the word genesis, it's going to be an anabolic reaction. So catabolic reactions do what again? They take large molecules and break them into small molecules. And anabolic reactions are the way we take small molecules and make them into large molecules. Then what we're going to do is put a precursor to that that's going to tell us the molecule. So in glycogenesis, where glyco is a reference to the end product, which is glycogen, And so in glycogenesis, what we're going to do is we're going to take extra glucose molecules and we're going to convert them to glycogen. Then we have two sets of tissues in our body that are experts at doing that. So skeletal muscle is an expert at taking glucose and converting it to glycogen and storing the sugar in a form in which we can retrieve the energy quicker. And then your liver. So our biggest stores of glycogen occur in our liver and occur in skeletal muscle. So if we have all the energy on board to run our metabolic processes, we have all of the structural components that we needed to make new cells and new cellular material, then once the liver and skeletal muscle have stored their supplies of glycogen, then adipose tissue takes up glucose. And instead of converting it to glycogen, converts it to a triglyceride or a fat. So that process is called lipogenesis. So adipose tissue is a specialist at taking sugar molecules and converting them to fat molecules, which is more long-term storage component. So because we store this sugar as a glycogen, and that's our quickest retrievable energy supply, then we also have a mechanism by which the liver and skeletal muscle can quickly break down glycogen, return it to glucose to make ATP. So that's called glycogenolysis, where we're going to take glycogen molecules and convert them back to glucose molecules. So one of the reasons why exercise is a key player in the ability to maintain body weight is you can force your skeletal muscle to undergo glycogenolysis doing exercise, so that when you eat, then instead of doing lipogenesis with the sugar, you do glycogenesis with the sugar to replace the ones out of your skeletal muscle. And that prevents your fat cells from doing so much lipolysis. That's one of the reasons why exercise is key to the process of weight loss, is just that simple mechanism. So if we were in a fasting or starving state where we had actually done our glycogenolysis and we've used up all our glycogen, then what we have to do is begin to break down fats and other things to actually use as a sugar base. So if lipogenesis is the formation of fat, then if we break down fat, it's going to be lipolysis. And we can also break down proteins. And what we do is we take a non-fat sugar and convert it to a sugar. So lactic acid is a waste product from anaerobic respiration can be used. We can digest proteins and recover individual amino acids, or we can do lipolysis of triglycerides and come back to the glucose molecule. So since we're actually taking a non-sugar and coming up with a sugar, it's called gluco because we're going to come up with a sugar. Genesis because we're going to form a sugar. But neo is the key to this word. It means a new sugar. So a sugar from a non-sugar. So the process of gluconeogenesis is what we have to do to make sugars from non-sugars. So essentially, to lose weight, you have to use up glycogen stores at a frequently enough basis that you actually have to do gluconeogenesis to maintain basal metabolic rates, and then you begin to use up your fat reserves. All right. So when you look at this, it's kind of a summary of what we just talked about. But I want you to pay attention because I've got another one that we're going to use that we're going to review. And so notice that the gastrointestinal tract is at the center of this one. And so what the key is there is you're in an absorptive phase. So you've ingested food, you've done the digestive process, and now you're in the absorptive phase. So you're picking up material from the lumen of the small intestine and large intestine and moving it into the blood. And so this is just trying to show you that what your body does while you're in the absorptive phase. So, for example, if you have, in the absorptive phase, then you're going to become hyperglycemic, so your blood sugar levels are going to go up. So, if you become hyperglycemic, what hormone is going to be released from the pancreas? Insulin, which is going to help our cells take up sugar and to process sugar. So one of the things that skeletal muscle would do is take up the glucose from the blood and do glycogenesis, which would produce glycogen out of it. So one of the purposes of this is to look at the last slide, and so that you can tell me what reaction 4 is. So reaction 4, going from glucose to glycogen, is glycogenesis, all right? So then the liver was an expert at that as well. So we have glucose from the blood going into the liver, and then over here we have glucose going to form glycogen. So this arrow represents glycogenesis again. All right. So notice that the other thing the liver is doing glucose and converting it to fatty acids, plus this molecule that's eventually going to be converted to a glycerol molecule, which allows us to convert it to a triglyceride. So these two reactions are subunits of a general reaction we just called lipogenesis. Okay, and then notice that same reaction's down here. So lipogenesis again, which is how we store fat if we have extra sugar on board. Okay? And then this oxidation is what we're going to talk about eventually, which is the mechanism of cellular respiration. So the Krebs cycle, electron transport system. So part of it, so this picture is showing us that as we're absorbing things, we're going to use, most tissues are going to oxidize the sugar to make ATP. Once we've got all the energy on board, then we're going to begin to store it in these mechanisms. And we're going to come back to the formation of ketones here in a second. But certainly what we would do both in the liver and in muscle mass is if we have enough energy on board, we're going to take amino acids and convert them into proteins, structural proteins. All right, so this is the pattern of gluconeogenesis, and we do gluconeogenesis so that we can run it through the Krebs cycle and make ATP out. Okay. So our normal pathway would be to take glucose, and then we're going to use some ATP to make the glucose molecule unstable by creating two intermediaries, so glucose 6-phosphate, which is eventually converted to pyruvic acid. And then on the surface membranes of the mitochondria, pyruvic acid, which occurs in the cytoplasm, is converted to acetyl-CoA, and acetyl-CoA is driven through the Krebs cycle to make energy out of it. So for gluconeogenesis to work, I either have to take a compound that I can convert to glucose and run it through this metabolic pathway, or come up with a compound that I can convert to a 3-carbon sugar or a 2-carbon sugar to drive it through the pathway. So the reason why I store fats is because I can store the highest amount of energy in a fat molecule. So that's why the body's chosen way to store long-term energy is fat, so in the formation of triglycerides. So in lipolysis, we're going to do it in kind of a stepwise fashion. So remember that in a triglyceride, we have a 3-carbon compound, which is our glycerol molecule. So this is our glycerol molecule. And then attached to that, we have these fatty acids. So in the process of lipolysis, so the enzyme we've talked about that's the expert at lipolysis would be a lipase. Okay. then what we're going to do is try to remove the glycerol molecule and free it up. And then what we're going to do is free up these 3 fatty acids. Okay. Well, the glycerol molecule is a 3-carbon compound. Pyruvic acid is a 3-carbon compound. So we can break down a fat and use the glycerol just like we were using pyruvic acid in this process of gluconeogenesis. So we can just simply use the 3-carbon compound as an energy source. The fatty acids are long carbon chains. And so what we're going to have to do is take a fatty acid and break it down into chunks that we can actually use. So what we do is we break the bond between every 2 carbons. And so this is called beta oxidation. And if we break it down into 2 carbon molecules, then we have the same carbon structure as an acetyl-CoA. So we actually use our glycerol, and we can run it through like pyruvic acid. We can take our fatty acids and do beta oxidation, and we end up with many 2-carbon compounds that are like acetyl-CoA that we can run through the Krebs cycle. So that's the beauty of storing energy as fat, is we have a mechanism by which we can run the fat through our normal pathway for making energy. So over here, the dilemma we have when we break down proteins is that we have these molecules that are long carbon-carbon nitrogen, carbon-carbon nitrogen. So what we do is protein catabolism. And what we're going to do is break the bond and free up individual amino acids. And then with the free amino acid, we have if we break this bond, now we have a 2-carbon compound that we can use to run through the Krebs cycle. But what we end up with is this amine. And in the amine, we can do 2 things with it. We can take the amine and use it to make new amino acids. Or we convert it to urea and get rid of it in our urine. Okay. So one of the diets that's come out, which really does allow people to lose weight fairly quickly, is a high protein, low carbohydrate diet. So you make a shift from the ingestion of fats and carbohydrates to mostly proteins. And then that forces your body into using amino acids, which it's not as effective at doing. But the end product is you have a lot of nitrogen you have to deal with, and has led to the death of people because of nitrogen toxicity and kidney damage. The dilemma with using that mechanism. But we can do it, and that's what you do in starvation, is you use these amino acids, convert them to a compound like acetyl-CoA to drive through the Krebs cycle. So let's kind of review the whole process of acquiring energy through that respiratory pathway that's the common pathway within our body itself. So the key is that we're going to start with a glucose molecule. And then the key to remember, it's 6 carbons. So we have 6 bonds that we can break apart and retrieve energy that the plant's stored. There's nothing in life that's free. So to initiate this process, we have to have energy, or we can't do it. So we're going to actually require 2 ATP to initiate the process. Because we're going to break bonds, we're going to retrieve energy, and so we need ADP that we can convert to ATP in the process. And then we need some electron-carrying molecules, because as we break the carbons, the electrons in a carbohydrate because carbon is a large molecule, then the hydrogen electrons spend more time down here around the carbon. So when you break the carbon-carbon bond, you're going to spin off hydrogen electrons. Okay? So you need NAD to carry the hydrogen electrons. So what we're going to do with the ATP is we're going to create intermediaries that we're going to take the ATP and we're going to convert it to ADP. Then what we're going to do is we're going to attach the phosphate to the sugar molecule. So our first intermediate is glucose 6-phosphate. And all we're saying in chemistry, and I'm going to, instead of drawing a cyclic sugar, which is what it would be in most biological molecule, in most biological systems, I'm going to draw it as a planar molecule. And that way, we can actually just number the carbons. And so what the name glucose 6-phosphate is telling us is that we added the phosphate to this carbon, the 6th carbon in the molecule.
Do you expect us to know DNL?
Pardon?
You don't expect us to know what the DNL is, right? The glucose. We're not going that far. Okay.
No, we're doing similar things.
Good. Okay.
Because I have a wide population of students, some that have a lot of chemistry, some that have no chemistry, so I try to make it simple. My chemists get mad at me every once in a while. I said, yeah, but half my class only takes 121, which you don't do any organic chemistry in, so how do I teach organic chemistry to people who have no background? So anyway. And then the next intermediate is a 6-carbon compound where it's restructured into a fructose molecule, but we're still going to have 6 carbons. We just change the shape of the ring. And so I've already got my first phosphate on the 6th carbon. And so now what I'm going to do is put the second phosphate on the first carbon. So now I'm going to have a molecule that has a phosphate on the first carbon and the 6th carbon. So then when I break it down into pyruvic acid, I'm going to end up with each molecule a mirror image of themselves in terms of having a 3-carbon compound with a phosphate on it, which is pyruvic acid. So what I'm going to end up with out of the process then is 2 of these 3-carbon compounds with a phosphate on it. And then once I begin to break this bond, which is a carbon-carbon bond, then I can release energy. So I'm going to release the energy from that carbon-carbon bond. And the energy from that carbon-carbon bond is going to allow us to convert ADP to ATP. And we're going to do 4 and 4. We use 2 here. So what we're going to end up with is a net gain of 2 ATP out of the process. And then because I have these electrons to contend with, then when I break this carbon-carbon bond, I'm going to actually need 2 NAD. Which I'm going to add the electrons to. So I'm going to make 2 NAD. Then what we do is we use the H at the end to remind us that the electrons are initially from hydrogen. Okay? So we're going to make 2 NADHs. So it's simple organic chemistry. Right. So this is kind of a summary chart of what we just did. So we're going to take glucose. We're going to use 2 ATP because we're going to phosphorylate the molecule twice. Once we phosphorylate it, we create an unstable intermediate that is easier to break down. And so then we're going to end up with our pyruvic acid, which is 3-carbon molecule. We're going to make 4 ATP, but because we use 2 ATP, our net gain to our cell is going to be 2 ATP. And then we're going to have these 2 NADHs formed from the process. So we do that in the cytoplasm of the cell. So the enzymes that allow us to do this process is in the cytoplasm of the cell. So this is all just done in the cytoplasm. And if we didn't have mitochondria, that's all we could do, is we could make 2 ATP per glucose molecule. And we probably could not ingest food fast enough to stay alive by just making 2 ATP per glucose molecule. So what we have to do then is we have to transfer the end product into our mitochondria. And for the mitochondria to do it, it has to have an input of oxygen. So if we have an input of oxygen, then we can generate a whole bunch more ATP. So the reason why we can't live in an oxygen-devoid environment is we can't make ATP fast enough at 2 ATP per glucose molecule to run our brain, our heart, and our other very important organs. So, pretty amazing. So you could demonstrate, it would be a bad demonstration, but if you went to Yakima, to Wenatchee, where all the apple growers are in the state of Washington, to make sure we have apples all year round instead of just in the fall like when I was a child, then they store apples in these big buildings where they suck all the oxygen out of the building and fill the building with nitrogen. That prevents the apples from aging and oxidizing. And then there's big warnings on the buildings: do not enter this building, blah, 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 blah. But you have about 4 minutes, then you're dead if you enter the building. Because there's no oxygen in there. They suck all the oxygen out to keep the apples from rotting. It's an amazing process. So now what we're going to do is we're going to talk about the mechanisms that are required for us to make ATP from mitochondria. So the first thing we have to do is we have to convert the pyruvic acid from a 3-carbon compound to a 2-carbon compound. Once we create the 2-carbon compound, we can run that through the Krebs cycle. And then we can take all the NADs that we make and we can convert those to ATPs within our mitochondria. So it's a 3-step process. So the first step in the process is taking our pyruvic acid, converting it back to CoA. And so what we're going to do is we're going to have our 3-carbon compound out here that's going to come through the membrane, and over here it's going to end up as a 2-carbon compound. So one of the waste products out of our mitochondria is a carbon dioxide from this process. Now, technically, if you break a carbon-carbon bond, you should have enough energy to make, you should release energy. But the way we made the molecule, we harnessed a lot of energy here. So we're going to make no ATP out of this process. So in other words, we don't have enough energy. So we have low energy, let's just say low energy. So we have no formation of ATP directly. But because we're breaking a carbon-carbon, we still have those hydrogen electrons that we can harness. So one of the things we will produce is by converting this process, we can use 2 NADHs and we can convert it to FADHs that we can make more energy out of. Okay? So we're going to use 2 NADHs and we're going to make a 2 NADs, we're going to make 2 NADHs out of it. So because we had 2 pyruvic acid from a glucose molecule, then we're going to do this twice. So we're actually going to make 1 ADH per molecule. Now what we're going to do is we're going to add a compound to this called coenzyme A. And so we need this molecule called coenzyme A that we're going to attach to our acetyl molecule. So we call it coenzyme A. So that's this process here. So we've added coenzyme A to each molecule, so we get 2 acetyl-CoA. We went from 3 carbons to 2 carbons, so we released 2 carbon dioxides. Because we broke carbon-carbon bonds and there were hydrogen ions involved, then we harness a hydrogen ion for each carbon-carbon bond that we break. So one NAD and one NADH per molecule. So we end up, the only thing we end up with then is a net gain of these out of this process. But now we have a molecule here that we can run through the Krebs cycle within the mitochondria. So the Krebs cycle is an amazing cycle, and so I always, when you teach, you always kind of debate at what level do the students need, try to match the level of needs. This is where my chemists, particularly the biochemists, say, you don't teach the Krebs cycle in enough detail. I say, yeah, but 90% of my students aren't researchers, and they don't need that detail. They just have to have an understanding of it, a basic understanding of it. So why is it a cycle? Because what we're going to do is we're going to take our coenzyme A, our acetyl-CoA, and we're going to attach it to this carbon molecule. And then what we're going to do is we're going to recreate the same carbon molecule. So it's a cycle because we use a molecule to attach something to and we recreate it. All right. So let's go to the next slide and we can get to some detail. All right. So the carbon molecule is an oxalate molecule. And then when I add the acetyl-CoA to it, I get oxaloacetic acid. So this is the 3 carbon compound I need. When I add this to it, and I get my oxaloacetic acid. Then what I'm going to generate then is this molecule back. Right? So what I need is this oxaloacetic acid. I'm going to add acetyl-CoA to it. And I'm going to create an intermediate called citric acid, which is why it's called the citric acid. Then essentially what I'm going to do is a bunch of biochemistry. And when I graduated from college, I knew every intermediate, every enzyme. I could recite it. 30 years later, because I'm not a researcher, I never looked it up. So I figure if you're not going into research, it's a great lesson in memorizing. As long as you know the basic mechanism, if you need it, you can look it up. All right. So what we're going to do is we're going to just rearrange it, and in several places we're going to break molecules to give off carbon dioxide. So remember, we're starting with 2 carbon molecules, and we have 2 of them. So what we're essentially going to do is generate carbon dioxide in 2 places. So our net gain is going to be 4 carbon dioxide. And then we have our 2 carbon dioxide from here, or 4 carbon dioxide from here. We've accounted for the 6 sugars we started. 6 carbons in the sugar we started. Okay? So, because we're breaking bonds, then we need our buddy NADH so that we can convert it to NAD to NADH. So what we're going to do is we can do that several places, so we're going to end up making 6. And then we have some electrons at a lower energy level, so we need FAD, which is another energy-carrying molecule, and we can generate FADH2 from that. So what you're going to see is we need 6 NADs, 2 FADs. So we're going to make 2 of these. And then, long story short, is we technically, if you want to get into the biochemistry, do not make ATP directly. So there's another molecule called GDP. And what we're going to do is we're going to take GDP, convert it to GTP. So we're going to need 2 GDPs. We're going to make 2 GTPs. Then what we're going to quickly do is convert the GTP to ATP. So like I said, how technical we like it. All right. So at the end, we're going to recreate our oxaloacetic acid. So that's this molecule. So that's why it's a cycle, because we use the the oxaloacetic acid we need to attach the 2-carbon molecule to, and at the end we're going to regenerate it so we can attach it. Amazing efficiency. If we had to generate that molecule all the time, we could lose weight faster because we'd have to spend more energy doing it. But for most of our existence, we didn't always have enough energy. So we're very efficient at what we do. So we're going to end up with 6NADH, 2FADH, 2GTP, and 4 carbon dioxide. So at this point, we have 2 ATP we made here. And we have 2 ATP we made here indirectly. So now the net gain to our cell at this point is 4 ATP. So the electron transport system then is the most important component of this whole process. Okay? So does everybody have this so I can erase it? So I should have made it smaller.
Why is it ATP?
Because it's one of those, how honest do you want to be or how much of a little white lie. So I choose not to make you know the enzymes, but to do it in a more honest way. So we make GTP first, then we can convert the GTP to ATP. So technically, from a biochemistry standpoint, we don't really generate ATP. But in all practical purposes, you can say ATP. But remember, we made our GTP. So if we look at our summary chart of what we just did, then here was our oxaloacetic acid. We added acetyl-CoA. I should have my carbon up there. A little apology. I told you I could. I actually lack one class of having a BS in chemistry as well. I forgot most of it. Okay. So then we're going to create citric acid as an intermediate. Then we're going to break off carbon dioxide. We're going to make ATP. So notice that this is a summary of 1. So you'd have to do this twice. That's what I did up there for you. Now, the beauty of this is that if we can come up with a 2-carbon compound, then we can run the citric acid cycle. And that's what I was trying to point out to you, is that our normal pathway is to use glucose. But the reason why we store fats is because we can do it with fats. And then we can also then use proteins to do it. So the high protein diet works because you don't have enough of this. You eventually use up enough of this, then it forces you to use this. Which is what we see in anorexics and people who are starving. So the electron transport system, which is where we're going to use all the NADH, is an oxidative phosphorylation process. Where what we're going to do is we're going to use electrons in a series of membrane-bound proteins, and we're going to pass the electrons. That's going to create some energy to drive the hydrogen protons through the membrane. And then we're going to use a protein pump to actually harness energy. Okay. So the way I like to do an analogy of that is that my membrane is like a stair step. And I have these 6 molecules involved in the stair step. And at the end of my 6 molecules is where oxygen is going to be. And so as the electrons are passed from one molecule to another, then if a molecule loses an electron, it is oxidized. If the molecule gains the electron, it is reduced. So it's an oxidation reduction process. Then we're eventually going to be able to phosphorylate molecules. So just as a quick review, then what we ended up with out of this whole process was 2NAD from glycolysis, 2NADH from conversion of pyruvic acid to enzyme, and then 6NADH from the citric acid cycle or carboxylic acid cycle. Okay. So the way to think about the stair step is that NADH enters here, and every two oxidative reductive processes gives me the energy to make an ATP. So remember, this is an analogy. This isn't actually the biochemistry, but it helps. I find it helps students remember. So the take-home message is for in every NADH, I will make how many ATP? 3. Then eventually what we're going to do is we're going to recombine the hydrogen electrons with hydrogen. And then we're going to combine the hydrogen with oxygen to make water. So then the beauty of this process is we end up with carbon dioxide as a waste product, and we end up with water as a waste product. And those are the two waste products that plants need to make more sugars in the future. So it's perfectly cycled. Which is beautiful. So all you have to do is breathe and pee in the woods, and then the plants have the material they need to make new things. All right. So how many do we have from glycolysis? NADHs. 2 NADHs. So how many ATP are we going to make in the electron transport system? 6 ATP. So how many do we have from the conversion of pyruvic acid to acetyl-CoA? 2. So how many ATP are we going to make? 6. And how many do we have from the Krebs cycle directly? Or indirectly? 2. 2. How many NADHs? 6 NADHs. Sorry to confuse you. We're in the Bahamas. And so 6 times 3 is 18 ATP. So just from the NADHs that we created, we're going to make 30 ATP. Okay. So what actually happens is FADH enters here in this analogy. So from FADH we can only make 2. So how many FADH do we have from glycolysis? How many FADHs do we have from pyruvic acid acetyl-CoA? None. So the only place we create FAD is the Krebs cycle. So we had 2 FADHs from the Krebs cycle. And how many ATP can we make? 2 for each one, so 4 ATP. So we end up with 34 ATP. It actually varies depending on the metabolic process between 32 and 34 out of our electron transport system. So here's the electron transport system. We totaled up 10 NADHs, 2 FADHs. We need 6 oxygens to do it. If we add that, we can get 32 ATP. And 2 water. 6 water. So this is what the stair step really represents, is a series of enzymes, membrane-bound proteins within the mitochondria. So here's where my NADA enters at the top of the stage. Here's where my FAD enters in the second step of the phase. We use these electrons to help drive hydrogen protons across the membrane. And then we have this proton pump. Then as the hydrogen ions fall back through, get reconnected with their electrons in the nucleus. So the stair step. This is a summary chart of everything we just did. So So if you know that, show me starts, we'll do that. Okay, so what we have left to do is a little bit of protein metabolism. So there was a name for what we talked about, I had up here earlier. So if you're using amino acids for energy, or if you have abundance of a certain amino acid you don't need, then what you want to do is you want to cleave this bond, and you end up with a 2-carbon compound plus the amine group. So this reaction is a deamination, where we remove the amine group from the 2-carbon or the acetyl group. So I say you have an abundance of one amino acid, but you need other amino acids to actually make a protein. We have 20 naturally occurring amino acids, 12 of which we can construct, 8 of which we cannot, that we need in our diet. So if you have this one, and it's one of the amino acids we can construct, then what we can do is cleave this amino acid so that we have our amine group. And then in another step, we can take this amine group and add it to another acetyl group with a different functional group and create a new amino acid. So this first step, we're removing it from our amino acid. This is a deamination. And then where we put it on a different one to make a new amino acid is a transamination. So we have two processes that we can do, and they're sequential processes, where we do a deamination first, and we put it on another molecule to make a non-essential amino acid, is a transamination. Then if we make new proteins by adding new amino acids together, it's protein synthesis. If we break down proteins by separating amino acids, it is protein metabolism. So we have maybe 5 slides left, so we'll finish in 1.